So I want to give a short introduction of yourself. So Nicholas McGuire will give us the next talk about robust predictive statistics for resolving the AI certification problem. So Nicholas is a very long follower of the FUSE functional safety community collaboration with us here, and he's very into the topic of maintaining of real-time Linux since several years, safety-related systems. We're almost nature to next step, and Nicholas is here together with his company OpenTech, working on several specific focus on utilization of floss and components of the shelf for safety-related applications. And today we are very happy that Nicholas will give us some insights about how to certify ANS and more specifically how machine learning classifiers could look like and some first promising results of his activities. So I will share the screen for this presentation. I hope this works now in full present mode. And now it's on the screen. Nicholas, the floor is yours. Thank you.
Thank you. As Helmut said right at the beginning, FuSaCom is open for good and bad examples. So we will know maybe in a year or two if I will be presenting a bad example or a good example today. It's quite speculative. It's quite early, so first results look promising, as Helmut just said, but I would say they are not yet in the shape to make too wild claims. I would like to point out more that it is a possible solution, and we will see, hopefully relatively soon. As Evan just showed us, there's a lot of standards. We have not been aligning with these standards except for 62158 and the SOTIF standard that I have been looking at, but we will not cover standards in this presentation. Yeah, go to the first one, please. The challenge of machine learning and functional safety, we have heard quite a bit about it today already. One of the big problems with applying classical methods is that a lot of the classical methods basically had the premises that software is deterministic, in the sense that for any given input, if you provide the same inputs, you will get the same outputs. Now, technically, that's of course even true for an AI-based systems, but we have a lot of random inputs in such systems, and practically you cannot actually control these random inputs, so they have a certain inherent non-determinism built in at the algorithmic level. And therefore, a lot of the classical methods don't really work there. Then we have the problem that we are talking about probabilities only, and we simply don't know the actual distributions. We have empirical distribution for ANNs, but we don't actually have specified or quantifiable distribution in most cases. Use of heuristics is more common. We heard about the standard process for AI that is basically design, test cycle, which is actually something that we have been frowning upon for decades now in software development, that you don't iteratively fix test, because that does not allow you to give guarantees for your results. Now we're back to that stage due to the limitations of AI that is below, or the AI theory. It is a very empirical genre. There's not a lot of theory behind it. At least, I mean, if you go back to symbolic AI, yes, there's a lot of theory there, but not if we're talking about deep learning and convolution neural networks. And that goes also very far, because if we look at really the very basic algorithms that we are using in machine learning and deep learning today, some of the prerequisites that are assumed there are not satisfied, like dot product actually assumes that you have linear relations and Gauss distributed noise. Both conditions are practically never met. And as we also heard, Evans noted some standards that are working on complex hardware. We have the problem that these hardware elements are extremely complex. So it would really not be very helpful if we had these certified. Even if I could give you a certified GPU, it would not really say much about the correctness of the results. Of course, if the GPU is broken, you might have bad results, but just because your GPU is certified, it just doesn't tell you much about your the output of your machine learning application. Next one, machine learning and correctness. That brings us right to that problem, is that we don't really have guarantees how these things will behave for new inputs. We heard that before as well. And of course, we can try and do it by explainability approaches of understanding machine learning, and therefore having at a qualitative level a predictive capability of saying, well, it will probably handle all similar images of trucks and so on and classify them correctly. Evan pointed out the security issues of adversarial attacks, and in the first presentation, I forgot if it was Moritz that pointed out that adversarial methods is an important issue, because we know that it's not just about new inputs, it's about inputs that are deliberately misusing or tampering with behaviors, is a emerging behaviors of these systems. And that's really the core of the problem, that the code does not encode the behavior. Hardware doesn't encode the behavior. The behavior of an AI is an emergent property of the system, and our current standards simply don't really address that. So even if I could give you a SIL 4 certificate, highly unlikely that this will ever happen, but let's say a mid-integrity certificate of a complex component like EDDL or TensorFlow or Keras, it really would not be very helpful to make any claims. So we need different strategies to get away from the code level, from the low-level hardware level, and get to the correctness properties of these emergent properties. Next one, problem statement.
Yes.
So from our perspective, our current assumption is that the actual challenge is that we have to cover extrapolation, which is not what current standards are doing. Current standards say you take a specification, you embody this specification in your element, you certify that the embodiment of this specification was done correctly, and then you apply it in an environment where this behavior that is covered by your specification is appropriate. And now we're in an environment where we have data-driven training to create an emergent property, but we actually have to extrapolate to yet unseen inputs, and we don't really have a lot of information about these inputs. So that's the sort of the paradigm change that's behind it. And we have to find some way how we can quantify that. As long as we cannot quantify it, we will have problems giving any guarantees. Next one, please, the expert problem.
Yes.
So the expert problem, that's not really AI, and we heard it before, and you will, if you work on AI and safety, you will see that a lot of the problems that we have with AI are actually more problems that we had previously on assessing humans and organizations, not so much technical systems. So maybe we can learn from these. But the expert problem really is that we are trying to do an abstraction. We're trying to automatically generate an abstraction that implies that we are dropping information, we are reducing information. We are therefore, by definition, almost avoiding complete coverage. At the same time, we have to give guarantees. Same thing with optimization. Optimizations are always in some way reducing or eliminating corner cases. And it's a well-known statement that all models are wrong, but some are useful. Now we have to figure out how to assess how useful is this model, or how wrong is tolerably wrong. And that's really what we have to figure out. We have to manage this discrepancy between an ideal distribution of an ANN, of classifying a certain set of classes correctly, to the real distribution, and these real distributions are simply not really known. And we currently have no way of deriving these distributions from, for instance, looking at the architecture or the parameterization hyperparameters of the ANNs, or certain qualities of the input data set. So we need different ways of doing it. Okay, next one.
Yes.
ANN decision uncertainty. So as we know from experts, from a single instance, it is actually very hard to say anything about the uncertainty. You can trust it or you cannot trust it, but you can't really quantify the uncertainty. So in traditional systems, we avoided this because we had deterministic properties of the system established by processes, and therefore while we physically might have a single system, we actually had an assurance that was based on a class of systems, and we just had one incarnation of this system. So we didn't have the single system problem. But now we have emergent properties based on training data, so we actually have a single system, and we cannot really derive much. So either we have to be able to find out how the distribution of a specific ML, the actual model, the training data, and the training procedure looks like, what it looks like, by having understandability built into these models, so that we can derive assurance from the process again. Or we have to find ways how we can force machine learning elements to be statistically well behaved. Currently, I personally think that the second path is definitely the one that's more realistic for now. There's a wealth of literature how to gain access to understanding machine learning that goes back all the way to the symbolic AI era, and even for the new machine learning, deep learning approaches. You can find quite a lot of publications on this topic. I don't think that they will reach quantifiability or assurance at the normative level. So I think the only way to go is that we have to use a way of forcing machine learning into robust distributions. And that is strongly related to the bias problem. Next one, please.
Yes.
Removing bias. So we have all sorts of bias sources, from labeling that is incorrect to labeled categories that are ambiguous. We see this in all data sets. That you find you have a data class truck, and I could ask 20 people to sort different images into the category truck and car, and I probably would not get totally homogeneous results. For some images of trucks, it's totally clear what the labeling is. For others, it's not so. The model design process was already talked about before, and that there's a higher uncertainty in the model design process. Basically, it's black magic still. If you take any AI book, they basically tell you, well, throw a few layers together, test it, tune the layers, use some pre-existing network that you might not even know what the layers look like. And it's a lot of tuning, heuristic-based tuning, but we can't quantify what uncertainty is this producing, what bias is it producing on the results. So removing bias means we have to break these implicit connections by decoupling model generation from specific problems, which is actually currently the case as well. I mean, if you look at a CNN for a specific problem, there's not much problem specific in there anyway, but the tuning process might be problem specific. And these feedback cycles are what we have to break. We have to remove these feedback cycles. So no test, fix, and adjustment. We just generate and use. We have to remove, ideally, or at least minimize human errors, because human errors are something that we cannot really quantify. In traditional systems, we also had human errors at the process level. That's why standards like 62158 have very extensive information about how to manage processes to minimize the probability of human errors going unnoticed. And now we have human errors in, for instance, the training data, but we don't really have control of the human error there. So next one, bias-free model hypothesis.
Yes.
So the hypothesis is actually, there is a proof for this under certain conditions from Robert Shapiro from 1990, that an syntactically correctly specified neural network trained on correctly labeled inputs, basically no matter how you train it and no matter how you design this network, will on average, and that's important to say, it's only on average, be better than a coin flip. For a single model that you generated this way, you really can't say anything. And that's one of the problems. So for a single model, we cannot really use this advantage that we have a guarantee of being better than a coin flip. But if we use a set of models, we can. So how do we eliminate these bias? We basically just randomize the hell out of it. The model architecture is randomized. The parameters, the optimizer is selected at random. The training set is a sample with or without replacement from a data set. The entire inference machinery is using image augmentation, traditional and some specific that we are playing with in different ways of image augmentation to remove any such bias as far as possible. So basically, we want to force it into a totally stochastic environment so that we can then use standard analytical and predictive statistics. So next one, please, overview of the HDM system.
Yes.
That's sort of the big picture what we have. We have a pool of models that we generated by randomly constructing eligible models, basically stacking layers of convolution, dropouts, and normalization, and so on. We take this pool, and the idea is that this pool ideally represents the infinite population of possible models. So we're sampling on this model pool. Then we take an image, we apply augmentation, standard augmentation. Here we're just showing the bit flips because the other augmentations are not really visible or well visible on small image representations. So we took the original image, we made it into a set of images, and now we apply this image set to each of the selected models, and then we get a prediction result, a prediction vector from each of the models for each of these augmented images, and then basically that's what you see at the bottom, that we have different, it's quite a messy business, and then we use basic statistics to assess if this herd of dumb models actually agreed in a reasonable way or not. You have to imagine this a little bit like you have the problem of figuring out the height of the room. You don't have a way to measure it, so you could ask 100 people. You get 100 estimates, but that doesn't give you any assurance. But if you can calculate the standard deviation of these 100 estimates, and you find out the average is 3 meters 20, and the standard deviation is plus minus 3 centimeters, then you could say, well, it's very highly unlikely that 100 randomly picked people would have such a small standard deviation if they don't have a common knowledge that allowed them to come to such similar results. So we're inferring the knowledge by looking at the statistic. That's really the core of the idea. Okay, next one, herd inference. So how do we do this? Herd inference, it's quite trivial. We have certain thresholds on the prediction that they are made they made in the prediction vector. We want to be better than a coin flip, so we select prediction values that are greater than 0.5, for instance. Then we take this from all models, take all the eligible results, stack them up into a matrix, and then we look at statistical properties of this matrix. If the statistical properties pass a certain threshold, then we can derive that there probably was a common knowledge in this herd, and we select the image, otherwise we reject it. So it's actually a very simple process. Let's look at some examples. Next one, please. So here's an example where we had 4 models, and if you look at the data, you see it's very messy data, and you might say, well, image on the left top misclassified and the rejected, they don't really look very different. And that's basically the idea, that you take a lot of models and then you can see it in the analytical statistics if you can trust the model or not. And that translates to the ability to actually then do statistics, predictive statistics, going even to unseen. We'll see the inputs. We'll see that in a moment. Okay, next one, same thing with 64 models.
Yes.
I'm not sure. I think it was 8 replicas of the image. So you see, it's not a very clean. This is truly dirty data science that we are doing here. We're just using very simple statistics at the moment, not because they're optimal, but because they are more understandable, and we do expect that we can do a lot more to evaluate these result matrices to get better performance out of the system. But performance at the moment is not my criteria. At the moment, we just want to have an AI that if it says this image is a horse, then we want to be able to give you a quantified guarantee that it is a horse with 99.99 probability. We're not anywhere near SIL 2 or SIL 3 quantities yet, so no 10 to the minus 6 or 10 to the minus 7 yet, but I do think they are in reach. So what does this look like? Next one, distribution, selected, misclassified, and rejected.
Yes.
That's not really the interesting plot, but we'll discuss it very briefly. Top left, in the background you have the small herd sizes, and in the foreground you have the large herd sizes, so herds with 32 models or 64, I'm not sure. And then we have on the x-axis we have the consensus. So consensus from one model to all 16 models agreed. And you see basically it's more or less an exponential decaying function. And between 15 and 16 you have this little peak. It's not very visible probably on this graph. I hope you can see it. And that's basically where you can see that with large herd size we get an increasing number of unanimously agreed results that do not follow this exponential decay function. For the misclassified, it's actually quite clear. The misclassified basically goes to 0. So we see if we have a single model and very small herds, then you have a very high misclassification rate, and if you have large herds and full consensus of the large herds, misclassification rate is basically 0. But the price of this is a very high rejection rate at the bottom. So currently these models have about an extraction rate of 6 to 8%, which is, of course, not very attractive for any practical application. But as I said, that's not the important plot. The important plot is our in distribution inputs. Now let's look at out of distribution input. Next one, distribution of misclassified rejected.
Yes.
So we took a second data set, the CFAR 100, and then looked at, ideally, if all of them are out of distribution or none of the classes match, you would see everything is rejected. And if you look at the left plot, you can see that it is basically rejecting almost everything. Not very visible, but I can tell you there is a small number at the large herds and unanimous consensus. There's a small peak, and those are collisions where we actually found images that it classified from the CFAR 100 data set in the CFAR 10 classes, and most of them are actually correct. That is, for instance, we had a house with a car in front of the house, and this image was classified as car. So it's a legitimate misclassification. There's some collisions, so to speak. But basically, we're approaching close to 100% rejection. And that's the key property compared to current ANNs. If you take the best CFAR 10 trained model, and we apply the CFAR 100 data set as input, it basically classifies almost all images, because ANN is basically a projection from every possible input onto your class vector. So no matter which input you present, it will select one of the classes as outputs, because ANNs don't really have the ability to say, I don't know. But we can teach them to say, I don't know, by looking at the herd response. And if the herd's response is not in agreement, then we can infer that they don't know what they're seeing. Okay, conclusions?
Yes.
Yeah. We have well-behaved statistics in herds. I must add that the currently used herds are quite large, not very attractive for any practical applications yet. But the important thing is that we have a possible avenue for quantified properties of correctness, so dumb models can do it. We just have to use quite a large number of them. The further benefit of the approach is that we have been experimenting with training on small data sets. With small data sets, I mean that we have been, for instance, training a model for MNIST digits where we only used 100 images for each digit, or the CFAR 10 where we're using 200 or 250 images for each class rather than 5,000. This is important for sort of going into a learning cycle. You have a first model that is not very efficient, but it extracts highly reliable data out of inputs, and then we can sort of grow the training set automatically. Yeah, so it is effective at selecting in-class images, but it is highly inefficient at the moment. We have handing in an EU project at the moment, a Pathfinder project, and hope to mitigate some of these. Yeah, from a safety perspective, I think the key issue is that we have path for introducing quantification, and we have a robust way of an ANN saying, I don't know. Not very attractive for the application if your autonomous vehicle would go into a safe state every 5 minutes. So performance has to be improved, but essentially that is one possible solution to the safety problem. It's a little bit like the SOTIF standard. What we're doing is we're looking at the ANN. Of course, that does not cover that TensorFlow or Keras or your GPU would have to be qualified according to usual standards. That's not eliminated just by having a quantification of the ANN behavior, but it is one essential step forward, I think, to allowing to use safety related ANNs.
Good. Thank you very much. So I think we thank again to Nicholas for this first results. I think you also said it. So this is still ongoing work here, and hopefully in a follow-up activities we could give some more insights in the next period here. Yeah. Thank you very much again.